All right, I guess it already started. Again, thank you for joining, especially the panelists and invited speakers of our workshop. And how this is going to work. So I'm going to ask some questions, and then I'm also going to ask the audience to prepare some questions or book them through the chat. And I invite all the invited speakers to have the camera open as well, if they want their mic when they talk, especially. And for the others, I would ask them to keep the microphone muted and open it just when I mention their name if they book let's say the question in the chat, or when I mention them as they if they want to give their question with their voice instead of writing that on the chat. All right, so let's start with the first question. But before that, let me introduce the panelists. So here we have Christopher Cannon, a senior AI scientist at Page and assistant professor at the Rochester Institute of Technology. Then we have Davide Mattoni, full professor at the University of Bologna. Subutai Ahmed, vice president of research at Numenta. Razvan Pascanu, research scientist at DeepMind. Gemma Roy, professor at Goethe University, Frankfurt. All right, so let's start right ahead with the first question, an introduction, let's say, to the panel. So in the last few years, the term continual learning has increasingly become more popular within the machine learning and deep learning community. Nevertheless, the definition, the objectives, and the importance of these learning paradigms are somehow differently interpreted. What's your definition of continual learning, and why do you think continual learning is particularly important for the future of machine learning? What are its relationships with other ideas used in the past under the names of online learning, incremental learning, and lifelong learning? And what are the relationships with other learning paradigms such as meta learning or reinforcement learning? So anyone here can take the reign and answer these questions. You're all invited to do so.
Okay, I guess I can go first, unless someone else wants to. Yes, I think we should really raise the stakes of continuous learning in the machine learning literature. I think continuous learning, if we want to build intelligent machines and truly intelligent machines, I think continuous learning is probably the most important problem we have to solve. And the reason I say that is there's so much effort on learning, lots and lots and lots of different tasks, but in a fixed way. And I think it's fundamental to the definition of intelligence that you be able to learn new things. And if you, no matter how many different topics you know and are good at, if you cannot learn one more thing, I would claim you're not intelligent. And so I think it's fundamental to the definition of intelligence, and it's a really hard problem to solve. And so that's sort of why I think it's important. And in terms of kind of a definition, I come from a neuroscience background, and we study neuroscience, and I would define it as something like something like what animals go through, which is you get a continuous stream of data coming in. There's no real training set or test set. You're constantly behaving and acting in the world, and every time new information comes in, you update and you get better and better and better. Of course, there's no catastrophic forgetting. You might have forgetting, but not catastrophic forgetting. And you can learn new things very, very efficiently. As you get new things that come in, you can leverage what you've known before and very quickly be able to work in, even in dynamically very different environments. And I think that definition is very different from the typical machine learning training set, test set definition. So I think we overall really need to raise the stakes of this and think of it as a crucial, important problem in creating intelligent machines.
I think that's pretty much this very similar answer to mine. I don't have like a concrete definition. I wish I did. But what I want to make is systems that learn like we do, that can learn over time without catastrophic forgetting, and that learn new tasks without forgetting old tasks. In my talk, if people have an opportunity to watch it, this is what I talk about. I talk about how all the different definitions that people are proposing for continual learning, and why even study continual learning, and how many of the problems people are studying don't really match our objectives. Like the reasons, the justification for studying this are not matched by the paradigms and problems people are proposing as methods to attack the problem. So I think we really got to move closer to something along the lines of no real training and test sets and new capabilities for things like knowing what you don't know, and really and learning from temporally correlated experiences rather than kind of like forcing data sets into strange, bizarre scenarios. And so a lot of the systems people test today for continual learning only work in those strange, bizarre scenarios. They won't actually work in a more mundane environment, which is kind of like you created a super solution for a problem, but you have no general solution. So I think we got a lot of work to do right now.
Yeah, so maybe I can add into this. I really like the analogy with neuroscience, and I'm very interested in finding these analogies with artificial intelligence and actual human or animal intelligence. And of course, continual learning is a key component of that. It comes, of course, the question of exactly which task the systems need to be learning and in which environment and so on. And just to make a relation in some of the parts of the question, which how is this related to active learning, transfer learning, knowledge transfer, and so on. So all these others, to me, are key components of continual learning. So continual learning is kind of englobing all this, because so there needs to be common knowledge in which you can transfer, of course, but without overwriting what you have learned before. So all of these previous paradigms, in a way, are important, but are too reductive to the continual learning, which is much more complete in a way, because we, at least that's my point, and what I hear as well is that it's more like how a biological being or an artificial, an intelligent being would learn in a changing environment.
Okay. Yeah. Okay. Okay. Let me try to give an answer from a slightly different perspective. I think deep learning, machine learning in general, has been relying a lot on parallelism, and I think a lot of other fields have so far. Continual learning is exactly the opposite of that. It's about how can you learn sequentially. And I think if you are to do this, you need to find a different way to learn or to optimize. And I guess in my talk I touched about this, and I say that for me personally, continual learning is about finding a different way to do credit assignment in a neural net, a different way to understand which parameters should represent which part of the function. And I think it's interesting sort of to answer the question, why do we care about this different, like we've been so successful at parallelizing things, why do we really want to learn things sequentially? And for me personally, just the fact that biological systems do that is not motivation enough. But I think there are two reasons that are usually given. One that most of the time is given is the fact that many times it's imposed by the world around us, by the environment. You know, things evolve over time. There's no way we can control it. There's no way we could paralyze this, and that's why we need to solve it. But the other aspect of it that I'm actually even more interested in is, I think if we manage to figure out how to learn sequentially, we can actually improve data efficiency considerably. I think a reason why a lot of the deep learning algorithms are not data efficient is because of this approach that we have, where everything is done in parallel. Like there's no explicit knowledge composition. You don't learn one aspect of a problem, then a different one, and then you just learn how to compose them. You have to have everything in parallel, and there's and because of that, you don't get sort of this forward transfer, this boost, which I think should really be the holy grail of continual learning, even though at the moment I don't think we've ever observed forward transfer or powerful forward transfer. And in terms of how this is related to other fields, I think this usually end up being sort of very technical differences. Like online learning to continual learning, I think it's the scale of the non-stationarity and so forth. So I think all of these fields there are very technical reasons, and that's why they have different names, and it should be like that. And it's important because you need to adapt to that. But in principle, many of these are in spirit trying to figure out the same thing, and potentially tools that we find for online learning should work in continual learning and the other way around. So we should keep an eye on these fields and kind of try to combine them as much as we can.
Just a few notes on the relationship between other fields. In general, I think that giving formal definition is very, very difficult. So I will not try to give formal definition for continual learning. And also the relationship between continual learning and the other fields like online learning, meta learning, and few-shot learning. I think that the relationship depends on the applications. So in different applications, these fields are close. In other applications are not so close. So in general, trying to fully extrapolate the relationship is very difficult. I think we should focus a little bit on the application and try to understand what are the relations.
Okay, thank you so much for answering this question. I remind the audience here that they can ask their question in the chat, or they can book their question, and they can, somehow raise their hand and they can start talking, unmuting their mic. So I guess we can move on to the next question while we wait for other questions from the other people joining in. And the second question is more about current challenges that we have in continual learning. So I would say since around 2015, I mean, hundreds of papers have been published in top-tier conferences, machine learning conferences, computer vision conferences, and journals proposing new approaches to address the problem of catastrophic forgetting. So at the moment, can the problem of catastrophic forgetting be considered solved? What are the main issues, biggest limitations, and current challenges in continual learning today?
I honestly don't know, in part because everybody's got all these different definitions. So I can tell you a recipe for solving catastrophic forgetting. If you have an infinite amount of memory and storage, you can just progressively fine-tune. It doesn't work as well as just in training from scratch, but the gap is very small. In a paper I published with one of my students, we were able to achieve on a bunch of data sets and different orderings doing this, 99% of the performance. Of course, then you're like, well, that's kind of unrealistic. That violates the whole point we're going to do this, is not to have infinite compute necessary and infinite memory for an infinitely growing data set that we store to disk. So, but if you do that, you get very close to solving it. You don't get much in the way of forward transfer or anything like that. But you solve the catastrophic forgetting issue. But it doesn't feel like the right solution, right? So it's really hard to say. Everybody's testing these, creating systems and testing them in very different ways. In my group has tried taking methods that people say work in one place and trying them out on different paradigms, and they just utterly fail. So it's really hard to know how much rock solid progress is being made.
Yeah, I really like that answer. And just I wanted to add, I think usually we have sort of this list of things we would hope a continual learning system would do. And I think many times, like, you cannot accommodate all of them. So for example, you can't expect the system not to forget, but at the same time have finite capacity or finite computation. Like, there needs to be some trade-offs. And I think the biggest issue with continual learning is in its definition, because there's no clear definition, and the definitions that we have and that we use don't give us any clue of what are the right trade-offs that we actually are aiming for. So you end up with lots of algorithms. They strike different trade-offs. They work for the particular setup they present in their paper and for the particular trade-offs that they target, but we don't know what trade-offs we want. So we either need to root the definition, or we need to root ourselves in a domain, in a problem that we think, okay, this is the problem we need to solve, or in a slightly different definition of continual learning that also allows us to figure out what is the trade-offs that we're looking for. And then we can know, like as pointed before, like, you can't say catastrophic forgetting has been solved, because it's trivial to solve it if you ignore everything else. But if you don't ignore them, then which ones can you ignore, and what trade-offs should you allow? And we don't know that.
Yeah, I would agree with both of those. And the point Chris made about efficiency, I think, is super important. So I don't think catastrophic forgetting is solved in the way we really want to solve it. And efficiency is paramount. And this idea of treating things continuously as streaming information coming in is really important. And I think not only do you have to solve it efficiently, there are times when you do need to forget, and you don't want to always remember the past. And a good example, one example of that might be, let's say you're going into your office building every day for years and years and years. Every day you go into your office building and you enter in a particular way. Well, one day they remodel it so that the front door is now off to the side, and now you have to enter through the side. You want to be able to learn that extremely quickly. If you treat it and compare against a batch system, well, a batch system, the first several years of this, the previous one is still going to be the preponderance of evidence. It's going to take you years to unlearn that one little path. So you should be able to actually very quickly forget it and think of it as a sequential problem. It should be far better than a batch system. I think comparing against a batch system is not the right metric. If you think about, and you should be able to adapt very quickly to this change, but not forget everything else about the building and how you got there as well. So here, efficiency and treating it as a kind of continuous problem I think those are key issues that are still yet to be fully addressed in the literature.
Yes, I agree. Actually, if you look at some publication, the gap between system trained offline on the entire data set and continual learning approaches is sometimes small. So one could think that the problem has been solved, but I think this is not the case. This depends by the fact that typically people use an oversimplification of the continual learning problem. And in fact, we are still far from a system that can be trained for a long time with small batches, with non-IED data, and so on. So the next point, Vincenzo, on benchmarking, I think is the crucial point. You should provide a realistic benchmark, not oversimplification of the problem, and invite researchers to work on that problem.
Yeah, so adding into the last point, that's what I wanted to say. So there, it seems that there is the need to have a more formal benchmark, and it can be broken into different trade-offs, as was said before, and have one that maybe contains all of them. Because of course, maybe at the beginning when you start tackling a problem, you cannot take everything into consideration, but then you can evaluate in which of these trade-offs your system is working on, in which it breaks. And then when you have different systems and you can identify which are the components that are essential for each of these measures or metrics in the standardization, then maybe you can combine them to tackle the overall problem.
Right. So we have a few questions actually in the chat. So I'm gonna read one of those. That is from Tyler Eyes, I guess one of the PhDs of Christopher, if I'm right. So she says, where do we draw the line between having one agent learn many tasks incrementally and potentially infinitely versus having many agents that can learn incrementally but are experts in a particular task? It has, do we, for example, do we expect to have one ideal lifelong learner for all the tasks, or potentially many incremental learners that are experts in subtasks like classification versus regression?
I
guess anyone can answer.
Yeah, I guess maybe as a first thought, at least in my mind, you can view, like you can have an ensemble of different agents that are learning subparts of the problem, and you can view them as a single agent as well. I mean, it's a sort of the same question as with tasks, like where does it start and where does it end? Just because they're modules that are learning different aspects of the problem, I guess it's a matter of semantics if they're one agent or if they're multiple agents. I guess it depends if they communicate or not. To me, again, I feel like one important aspect of it would be if there is some forward transfer. Like I'm fine to have a system that's composed of many modules that are learning separately, but somehow they should help each other, or somehow you should observe like that they learn faster because they know of the existence of each other. Yeah.
Yeah, I would agree with that completely. I think it's fine to have an ensemble of stuff, but it's not always clear you can discretely categorize everything into these independent tasks. And you need to have synergy and learning from each other as well. And one example might be, suppose you have systems that you know how to learn to ride a bike, or you know how to drive a car, but now you're given an electric bike. You have aspects of both, and you should be able to just instantly learn it and use it. You don't want to have to completely learn everything from scratch. You have bits of both in there. So figuring out how to seamlessly interoperate and cooperate and transfer learning and leverage your previous learning to learn new things is really the key problem. And whether you have multiple agents or a single agent, I think that's an implementation detail.
Yeah, so I was about to say something along the same line. So as long as the different agents can help each other in transferring the knowledge and learning faster, then it's okay to have multiple agents. It is not the same as having multiple agents that don't communicate and that learn from scratch. And here there are these trade-offs that also comes into the efficiency and memory, computational usage, and so on and so forth.
Great. So I think we can ask Razvan, in this case, a simple question, and then we can move to the next prepared, let's say, question. I guess this is from Pau Rodriguez. One question I can ask about crediting assignment to Razvan. Do you think that variants of backprop, I guess, would solve the problem?
Yes. So I guess I would be excited to find other approaches to learning that are not gradient-based, though I'm very skeptical of the ones we know. Like, I think gradient-based are by far the ones that are the fastest, or that leads to fastest convergence. There is an issue with how backprop does credit assignment, and it's hard to solve, though you could imagine things like coordinate descent, where you localize the updates to small subsets of parameters. I don't know exactly how you pick which coordinates would be affected by which examples, but I think there is hope to still use gradients, but somehow end up doing a different style of credit assignment. But I don't have a solution.
Great. So let's go to the next question. This is probably going to be an heated, let's say, question, especially given the, I would say, harsh critic from Chris Cannon in his invited talk about some benchmarks. So most continual learning approaches are tested today in classic, let's say, computer vision data sets, such as MNIST, Cipher, and ImageNet splits in several tasks or batches. Do you think these data sets are appropriate and enough, let's say, in order to benchmark the performance of a continual learning algorithm? And are the protocols and metrics used until today sufficient to objectively assess the performance of an original continual learning strategy?
Well, that's what my talk's about. So I have opinions. But no, I don't think the current tests, I mean, some of them I think are just kind of, I think in my talk I use the word pointless. But so some of them just seem kind of bizarre and strange scenarios. Others, though, I think have a lot of value, but as tests of a system, right? They're tests of capability. And sometimes I think that people building, not the people necessarily, but the systems devised for the test and not necessarily as a general solution. Like what I would love, I mean, there's a lot of, take ImageNet, for example. So as far as something like permuted MNIST, I don't think that's very valuable. Even using the task labels for like supervised continual learning, a lot of the task label stuff that people are doing, I'm not sure if it's adding much value today, where we are today in the field. In the computer vision community, since this is a CVPR workshop, there are a lot of papers nowadays doing incremental learning of classes in order on ImageNet, sort of. There's a lot of caveats there, but they use these giant batches. But what's important about those methods, though, is they're actually so rigid that the authors never even devised solutions that can train if the classes are revisited. they can't handle class revisiting. Maybe you could just tweak the algorithm in a few ways, but in the paper or in their code, it fails. It won't run. So it's like it's too rigid. So I think we need to develop like a comprehensive test of suite and know what we want to test to make real progress, and also figure out how we want to keep things fair. Like it's really hard. I don't have perfect solutions. Especially if you want to make something really interesting and novel, then I think in the computer vision field, a lot of everybody's using like ResNet 18. So we all use ResNet 18. What if I need to do something else to solve this problem? Then it's now going to become a lot, how do I compare against that? My reviewers will say I did something unfair. So I'll stop there. I have a lot to say about this in my talk.
Maybe I can add a little bit. I totally agree. I think many of the benchmarks are not that useful, or they might be misleading. I wanted to add two things. I think one particular issue is we need to define the different flavors of continual learning we care about in order to figure out what would be good benchmarks for it. So I think as it stands right now, many times continual learning is ill-defined and we don't know exactly what we want from the system. And that makes it really hard to come up with a benchmark that is good. And the other aspect that makes everything so painful is that because continual learning is about learning sequentially, that makes everything very expensive computationally and time-wise. So it's easy to come up with an extremely hard scenario that would take, I don't know, months to train on a cluster to see if it works or not, but to know that it's the real problem. It's harder to come up with benchmarks that researchers can afford to run, especially people in academia that might not have access to the same kind of compute, that runs overnight or that runs in 2 days or whatever, something reasonable, and at the same time tests the things we care about. So actually coming up with meaningful benchmarks, I think it's really, really hard. And we might first need to come up with good definitions of continual learning to guide us to come up with that cheap benchmark that we can run.
On the benchmark, yes, I agree that most of the benchmark used today are not appropriate because sometimes they are too small. The case for MNIST and CFAR. Also, the number of incremental batches is typically small, 5, 10, 25. And also, if you go to ImageNet, it's not good because the instances of the same class are independent, totally independent. So, for example, if you like to learn object recognition, learn to recognize objects under different poses, under different lightings, this ImageNet is not good. Typically, the models trained on ImageNet learns local textures, not the real objects with the shape and so on. So I think that we should focus on on application, try to understand what you would like to learn, and then define appropriate benchmark for this application. Of course, taking into account the efficiency and all the other constraints of the real application.
Anyone else wants to add something? Otherwise, we will move to the next question. Actually, we have a lot of questions coming in. So I guess we can move on. Gemma, you wanted to say something?
No, I just wanted to say that also putting emphasis on how it's evaluated, and especially in the computer vision community, that the same system, even with the same data set, using different kind of transformations for the continual learning approach or evaluation gives very different results. Like it's not the same permuting MNIS than really doing incremental learning of one class one at a time, or doing rotation and so on and so forth. So also which kind of input is used is very important.
Maybe one thing that I forgot to add, like I think another big issue is that we actually measure several things and we don't know how to combine them to a single number. And usually, when it comes to benchmarks, it's always useful to have one number to be able to compare things. It's unclear if you could ever combine all of these things, like the amount of forgetting, the amount of word transfer, the capacity used, and so forth. It's unclear you can actually combine them to a single number. But in terms of just benchmarking, it's really hard when you have these different axes and you don't know how to treat them.
Yeah. Right. We kind of tried to do that during the challenge that we had in this workshop, trying to combine different metrics. I agree that it's super complex to do that in a, let's say, fair way. Also because we don't know what, how well the different sensibilities for these metrics are not clear and are different. So it's difficult to find maybe weights for every metric and combine them to just one. Okay, so we have a question from German, I guess, German Parisi. Regarding the first question, I strangely agree with all answers because I see them as complementary. I strongly agree with Subutai on the importance of studying the biological aspects of learning to achieve AGI. But I also see Razvan's point that more technical solutions not consistent with biology are also good. Christopher's point, though, is crucial so that the community starts focusing on solving the right problem. My question then is, what's a well-defined framework and benchmark for the continual learning community to use as a stepping stone towards tackling continual learning in complex scenarios?
Yeah, I could. It sort of very overlaps with what we just discussed, and I think you and David have put a lot of effort into Core 50 and other benchmarks. As some of you may know, we also put out something called the Numenta Anomaly Detection Benchmark, which is a real-world complex benchmark designed for streaming data scenarios. And some of the unique things we tried to do there was we have a ton of real-world data from actual customers who are struggling with how to deploy machine learning systems. It's an incremental one where we're always trying to predict what's happening next. There's no explicit test set or training set. And another unique thing we did there was we insisted that there was no kind of manual parameter tuning for every new scenario. So we have dozens of different domains in the thing, and for every domain you start from scratch and you train as you go, and the exact same system and parameters has to work across all the domains. And I think this tries to get at kind of the transfer learning and the generality of the solutions. So I think those are kind of real world constraints and that we heard from customers in sort of very complex scenarios to this question. And we tried to incorporate in a benchmark. It's a kind of a small benchmark in today's standards, so I wouldn't say it's the best benchmark, but we tried. There's some kind of unique things to it, I think, that point to some real world complex scenarios.
Well, I think what's really tricky about specifying a benchmark problem is that issue I got at the beginning of just what if you give your system infinite resources, or at least much more resources than the thing you're comparing against. So so it's not just about the problem as in the data set, but also in figuring out what are you allowed to do as far as the system you're trying to use to solve the problem, and how do you make that a fair comparison in setting it up on a particular data set. But one thing, so that's a major issue, and I don't have concrete answers. I've tried to do that in all my work, but it's non-trivial. But regarding the data sets themselves, what I would love is something like, and we have a paper in this workshop trying to take some steps in this direction. And I think Core 50 is also a good step in this direction, but much like larger many-class data sets with, this is for supervised continual learning, not for the reinforcement learning, where it's also a little different, but also still have a lot of the same problems. Temporarily correlated streams of data that you're trying to learn from, and you assume that the system will be tested at any time, and it even needs to know what it doesn't know. And we need to have established protocols so that whenever somebody does have a benchmark, they're not just brewing their own thing in their own paper and they change the order of the data somehow, or change the setup at the beginning. Like, you really have to dig into the devil in the details for every paper and really need to re-implement it almost yourself today for all the comparison methods, or you probably aren't going to be able to do a fair comparison.
German, I think that it would be very nice to have a good benchmark for everything, but I think it is not much realistic because it depends. There are many applications for continuous learning, so I think that we need more benchmarks, and researchers should use the most appropriate for their intended scope and application. Also, MNIST is valuable. For example, if you have a very new idea of a very complex models that cannot be trained with large images. So in that case, just to move the first steps, maybe you can use even a simple data set. So I think we unfortunately we cannot use just one for everything.
Right. So let's move to the next question about, I think we addressed this somehow, but I think it's important to delve into it, about the biological, let's say, inspiration of continual learning. So the human brain is undoubtedly the most efficient and effective learning system we know of today. Much research in the context of AI has been inspired by biological insights and neuroscience discoveries, such as recent deep learning revolution, right? Will the same happen for the field of continual learning? What can we learn from neuroscience about the continual learning process happening in the brain? And are current continual learning techniques biologically plausible? And what if they are not?
Okay, maybe I can start, and then people that have more of a neuroscience background, they can actually answer this properly. I think there are quite a few approaches in continual learning actually are already inspired from biology. But I guess it depends a lot of, I'm always struggling with this parallelism with biological system. I think it's useful to get inspiration from wherever you can, and any inspiration is useful as much as you make progress. But like, I don't think we should strive to imitate biological systems. I don't think that's the point. I think the point is for us to get systems that can learn sequentially in an efficient way. And I think, you know, going forward, there are going to be more approaches inspired from biology. At the same time, there's going to be approaches that are not inspired from biology. Many things that are inspired from biology, even in deep learning, like, I don't know, ConvNets, which is the typical example, you know, you could explain them from a biological perspective, but they could be extremely well motivated from completely different perspectives, like, you know, in terms of representational power, like you can take a very analytical or mathematical approach to it, and then it comes out that you need to do exact convolution. So just taking biology is not the only source of inspiration that you can have, but it's definitely a valid one, and we should use it if it's close to us, or if we.
Yeah, so I just want to second that. I totally agree that it's kind of two different animals that can have a lot of interaction. And it can also be the other way around. So I've been seeing a lot of machine learning models now that are being used to trying to make sense of what's going on in the brain. So if we are tackling this problem, then we really need to focus on really trying to mimic or to model exactly what's happening in the human brain, for instance, especially in development, in the adult's life, when people are learning a new object, but they have a more consolidated knowledge, for instance. So these are kind of two phases. But if we only focus on machine learning per se, I agree that we can get a lot of inspiration. For instance, I think that this continuous learning concept, it can kind of have a flavor that it got inspired from how we learn. For instance, if we are able to do it, why not machines should also be able to do it? But it doesn't mean that we have to do it exactly in the same ways, because maybe our applications are different from how our capabilities are. So maybe we want that they are better, because we do forget a lot, and we kind of elucidate a lot of things that actually didn't happen, but we remember so vividly. So I think there are these two kind of trade-offs when we compare to actual biological intelligence and machine learning or AI.
Yeah, so you know, my whole talk is on some of the stuff we can learn from neuroscience and continuous learning. So I think there's a lot we can learn. I think it's important to underscore that we're not trying to imitate biology exactly. I think that's not the point. I think the point is to kind of uncover fundamental computational principles that we can learn from neuroscience and then apply them to machine learning. I think that's where And the reason to look at neuroscience is that, of course, humans and animals in general solve the continuous learning problem so well. It's so different from what's going on in machine learning that, yes, I mean, maybe we could come up at the solutions just from first principles, but so far we haven't been able to do it. A lot of there's stuff in the neuroscience community that's really valuable that they've figured out, that I think if we can understand the computational principles, we should be able to do it. Having said that, I know it's really hard. Neuroscientists don't think computationally. They're not often very good at explaining things in a computational way. So we really need to have, people really come together and a dialogue between the two so we can uncover, underlying principles and things that we can sort of transfer over to machine learning. And in my talk, I tried to talk about a few different things and try to describe it at a computational level. But if you were to read the actual papers in neuroscience of the stuff I'm talking about, you wouldn't have no clue what they're talking about. It's really hard to do that transfer, but I think it's super important.
Well, neuroscience is not my playground. In general, when I need to solve a problem, I tend to be quite pragmatic, so try to use an engineering approach. But I think there should be a better way to deal with forgetting than explicitly storing part of the old data in raw format. This is not what our brain is doing. I think that we can use some biologically inspired techniques to try to improve this replay or rehearsal techniques looking at neuroscience studies.
Well, I agree with everything that everybody said. I sometimes I say things like, the reason I study this is because I want to make systems learn like we do. And I also say things about new applications that would be enabled by this work. But when I say I want to make systems learn like we do, I don't mean how we do it. I mean just giving them the capability to learn from temporally correlated streams of data throughout a lifetime in an efficient way. So that's my motivation, and that's what I think we need to do. But I also have a background in computational neuroscience, so I try to draw a lot of inspiration from that. A lot of my papers are all inspired by it, but I'm happy with just solving the problem.
It's really funny when you look at neuroscientists and when they're studying learning, or what they call plasticity. There's no concept of batch learning. Everything is continuous. It's hard for them to even understand what batch learning is. No animal learns in a batch way. And there's no such thing as hyperparameter tuning, or neuroscientists don't understand what hyperparameter tuning is. Biological animals just grow up and learn. They don't have to have to go through the whole evolutionary process for every new data set or every new domain. So it's pretty funny when you try to talk about the importance of continuous learning with neuroscientists. They don't even realize that's even a problem. So it's quite interesting, I find.
Absolutely. So let's move to the next question about real-world applications of continual learning. So continual learning nowadays is mostly seen as an interesting and futuristic, let's say, research rather than a usable technology for real-world applications. In fact, many companies today, I think that Chris referred to this in his talk as well, prefer to use cloud infrastructure to store all the data and eventually retrain and redeploy the predictive models from scratch in order to maximize the accuracy performance rather than efficiency. So is continual learning just an academic, let's say, exercise? What are, in your opinion, interesting applications where continual learning could be particularly useful today, and why? Do you see a pervasive use of continual learning techniques in the near future?
Maybe I can say a word on this. I think even the thing that you mentioned, like, yes, it's true that companies right now, they collect lots of data, they retrain the model and redeploy it every time. That's actually quite an expensive process. If
Right.
they could, and I've seen this being talked many times, if they could just get the new data, fine-tune the model they have on the new data and redeploy that and save a lot of compute and a lot of energy, they would be extremely happy, and there would be a lot of money into that. So they're definitely interested into that. They don't have a solution that works. We don't have a solution that works that we can give to them that works better than what they're doing, but they're paying a cost. So it is a practical application now that companies would be interested in. There's also issues around privacy and all this kind of stuff where they're forced to delete data, but they would want that model to still have some knowledge about the data that was deleted that it's hard to get around. So there are legal reasons why a continual learning system would be more beneficial for companies. The other thing that I would say, in my mind, like real world application, like if we understand how to learn sequentially better, we would have more efficient learning, which I think is important for things like future learning. So I think in long term, like solution for continual learning would go so far as affecting things like few-shot learning or adapting very quickly to few examples. And then you have things like reinforcement learning, where understanding how to learn from correlated data, I mean, the amount of data you need right now in RL to learn is orders of magnitude higher than whatever you use in supervised settings. So if you can reduce that by a few orders of magnitude by understanding how to learn from correlated data, like RL could become practical. And there are many real problems that is hard for us to phrase as supervised, but it's quite easy to phrase them as RL. We don't do that because it's not as efficient. So I think there are many, close by applications we could.
Yeah, so I totally agree. I just wanted to add something that I've been thinking about, and I think it's a lot on our minds lately, which is it would be more green as well. So the fact that it has less computational power, it means that we would need less energy. And I think this is a pressing issue that as a community, not only in computer science, but as a scientific community, we are very concerned about it. And this could be one of the approaches in which we could also focus to try to tackle this issue.
I think there are several applications that can nowadays benefits from continual learning. One is robotic vision. Another class of application, I think, are those where you can deploy a pre-trained model, but then the environment is different for every deployment. So you need a sort of local adaptation. For example, if you consider surveillance, outdoor camera for surveillance, then you know that typically there are a lot of false alarms outdoor. So you can deploy an initial solution, but then depending on the environment, probably the smart camera should be able to filter out these false alarms and improve during, and this is optimal, I think, for continual learning.
Yeah, I think there are a lot of, I would agree with that. There are a lot of applications which kind of fall into that kind of general category of, more generally, maybe think of Internet of Things kind of things where you're deploying systems locally, in lots of different, in a variety of different environments. And you're getting streaming data in, but every environment has its own unique characteristics. And you need to learn about, in order to operate efficiently in that area, you need to learn about that, the specific characteristics of each environment uniquely. And there's no way a centralized system would be efficient at that. Each system is going to learn differently. You can't just learn, take data from across all of the different sensors and do it. You want to customize to each different environment. Take the camera example is a great one. There are many other examples like that of just sensory systems that need to predict and work and detect anomalies that are very local to environments. And I think as Internet of Things become more and more popular, continuous learning is going to be a requirement. I don't think you can do it in a batch way.
I think, so again, I agree with everything everybody said, but one big application that's I think this could help with is learning on embedded and resource constrained devices, unless you need them to be an Internet of Things and need to plug into the internet and upload to do all the learning. But this is really useful. This also can be more secure, I mean, in a sense, because then nobody can get access to the thing. If they can hack it, they have to physically get access to the object, right? And this is important. There was a toy company in Europe who had like a camera that uploaded the data to the cloud for analysis. So it's for kids, right? So the kids, this is like a little smart toy, uploads the data to the cloud with the kids. They got hacked, and so people got access to this kid stuff. The company got fined $500 million. So, so it's like, this could have avoided this if they were just learning on device and stuff like that. So there are applications like that.
Right. So let's get on with the last, let's say, open question I have prepared, and then we can move to the at least the questions that we can address in the chat. So what's next in continual learning? Once we get past current challenges and limitations of our continual learning systems, what will be the future of continual learning? What will we be able to accomplish in the midterm and in the long-term future? What are the next stages of this field?
So I think one thing that's going to happen over the next few years is there are going to be different flavors of continual learning emerging. So just to give like one thing that's sort of bugging me sometimes is a lot of times in continual learning, there's this underlying assumption that you can actually solve all the tasks. There exists a model that can solve all the tasks, and this doesn't need to be true. And potentially there are many real applications where this is not true. There's no multitask solution for this problem. And then continual, like then catastrophic forgetting doesn't make any sense because you can't remember things because they're in direct opposition to each other. And then this could lead to a very different flavor of continual learning that has some kind of task inference process into it, and it feels a little bit more like meta learning, but it's not everything in parallel. So this could be like a variant of continual learning that emerges. There are good reasons to believe that there exists a multitask solution, and then there's going to be the traditional flavor of continual learning. And I'm sure many other things like this would happen over the next year, like many different flavors. What I'm hoping though is that people actually formulate them more specifically, and there's like good definition so that we know actually what we're talking about. But I believe it's going to segment away into this kind of different things. And long term, what I would really hope continual learning to do for us is to help us understand how learning works. Particularly, I'm very biased towards neural nets. I really like them, and I really want to understand them. So, and I think we don't have a very good understanding of how learning really works. And I believe continual learning can help us, like understand how credit assignment can be done better, and things like this. So I think it really can help us do this.
Yeah, so I think there are a lot of challenges in front of us. So let's assume, for example, that catastrophic forgetting is solved. That we've completely solved that problem. The best ways of doing it. What's next after that? I think one of the big challenges is going to be something I call sort of continuous transfer learning. And what I mean by that is, as you're learning, as you come across new domains and new tasks, you get better and better incrementally at solving each new one. That is, you can leverage all of the stuff you've known before, and can more and more efficiently learn each new task compared to just learning that task from the beginning. And so this is something humans do very, very well. You can give me a completely new object that I've never seen before, and in one example, I will have learned a lot about it, and I can reason about it, and I can do things about it. And we should be aiming towards a system which can very efficiently do transfer learning as it learns more and more and more stuff. And I think that's going to be a really important challenge, is continuous transfer learning.
Well, again, for the future, I insist that one of the most important things is defining better benchmarks focused on real application, because there are several brilliant minds in the machine learning and computer vision communities. So we provide them clear goals, they can provide very efficient solutions, but we should agree as a community on the goals and the benchmark, and make them public so that young researchers can work on them.
Yeah, so I think creating benchmarks, even though it's hard and maybe one measure, it's not enough for measuring all the different trade-offs. It's probably we'll have different of them, and then at some point will converge. So I think in the more future, so more in the far future, so what I would like to see is something like a virtual environment that can kind of mimic how the trajectory goes from young AI, let's say, to a more adult AI. Because going back to the inspiration we get from humans, there are some experiments in which people record what toddlers see during their first year of life, for instance, and they really see their objects and everything right at their face. So it's kind of much easier for them to learn. Whereas parents, they see the objects and of course all the room much farther, so they can adapt, so they can identify very quickly a new object. But there's been all this process of learning during all the lifetime. And I think it would be desirable to try to mimic a virtual environment that resembles this kind of learning scenario. I know it's very difficult, and I don't know how to begin, but it's something that I would like at least to put on the table for people to think about.
I like the idea in principle. It's just, I'd love for an agent to be able to have a virtual life. You know, this is your life. Do your best. I think there's like a Rick and Morty episode about this. The near term, what I really want to see is not just one benchmark, but like a battery of tests and better definitions of what we want and fairer comparisons among systems. And somehow we got to control for that. Like as a field, I don't feel like we're doing a great job. And a lot of systems are just not even, they're just slight modifications of each other. So in this space, and they're being tested on exactly the same benchmarks, exactly the same problems, without really starting to expand the scope and try very adjacent problems. Like you shouldn't only be able to learn data in class ordering. You should be able to learn from temporally correlated instances. You should be able to learn if the data is actually shuffled. I mean, the system should only fail in that scenario because it's only been designed for the one setting. But the biggest challenge, I think, is just figuring out a way to make better systems. I mean, not the biggest challenge, but the biggest thing missing, I think, today is we don't really have tasks that we are measuring forward transfer effectively. We aren't really building compositional systems that are able to like composite and really like build representations that aren't just it's just like function approximation, right? It's just like finding something close by and predicting it. I don't think it's like the right approach. We need some sort of intermediate representations that are reusable, that can be transferred forward in the networks themselves. Then these representations need to be learned in a continuous way. Something like that, I think, is going to be necessary for us to get better sample efficiency. I mean, as you know, I like the developmental approach because as children level up a lot in skills as they age, and presumably the reason why we're able to learn new things more quickly in some sense for some kinds of problems as adults is we're able to leverage all that transfer learning. Of course, for other problems where the transfer learning isn't as effective, language, for instance, we tend to not be able to learn very well as adults. So, but I think there's something there for the forward transfer that's totally missing from the way we're currently doing this.
All right, so we're currently reaching the end of this panel, but if the panelists want, we can extend it like another 15 minutes. Because we have the invited talks from Chelsea Finn in half an hour. But I guess another 15 minutes, if you agree, we can extend this panel since I am enjoying so much. So we have a question from Roger. Could you please provide some more tasks that need continual learning rather than current deep learning methods? I mean, that is symbolic AI approaches, etc. Also, it seems that even for one task, continual learning cannot work well. Do we need focus much on multitask continual learning problem? If so, the task ID seems another problem. Anyone wants to take this question?
I'm not sure if I fully understood, but yeah, I guess any kind of system that is learning using gradient-based methods would suffer from kind of similar issues that like what we technically call continual learning, catastrophic forgetting, and so forth. So it doesn't need to be a neural net as long as learning happens gradient-based. I'm not that familiar with symbolic AI and the approaches there. So it's hard for me to say if those would need if those would suffer from this kind of phenomena. But yeah, I don't know. I guess the question was more than these two. What else is there besides these two? Yeah. And I didn't fully understand the part with multitask versus single task. I mean, I guess it's less important to me whether in the sequential, each part of the sequence is a multitask, and you go through a sequence of different multitask things. Or if you go I think these are just like semantics, and it doesn't really matter. Yeah, it's depending maybe on the setup, there is some important aspect of it, but in general, it doesn't matter.
I think that if you look at the real application, multitask setting where you have to provide the task label as not many practical application like incremental class learning or incremental problems. Because of course, as we said before, you can use an ensemble of experts to solve a multitask problem if you can, at inference time, understand what is your task. Of course, using a single model can have some advantages in terms of storage, in terms of size of the model, in terms of the forward transfer. But if you look at the real problem, real application, I think that incremental task, single incremental task has many more applications.
Right. So we have another question from Ali Ayub. Should we stop comparing the continual learning systems with deep learning baselines that are trained in a batch manner? Most of the papers publish results on a particular set of data sets, and if we test them on others, they show quite different performance. I think we also need to agree on a set of benchmark data sets so that it is easier to compare different methodologies. What do you think about this?
I don't think it's necessarily, well, so let's assume we can't do any of this forward transfer, right? And that we're going to ignore that. So let's just assume we want to overcome catastrophic forgetting. And I don't think it's unreasonable to compare a system trained in a way where the data has been structured in some order that will induce catastrophic forgetting to an offline trained system, and to measure the gap as like something else you do in your paper. I don't think there's anything wrong with that if that's what the question asker was asking. There was a part 2 to that question. Is that?
Yeah, you can read the full question on the chat. I'm reading from the chat, but he says, I think we should agree on a set of benchmark data sets so that it is easier to compare different methodologies.
I agree with that. And protocols, not just benchmarks, not just the data set. This is all about the sequence, right? All about the order. So we need to pay attention to that too, and probably something about compute and memory resources that are allowed for an agent.
I mean, I actually think that we should care about this forward transfer, and we should compare to the offline method. And I think as long as we don't get faster learning, we're kind of failing at continual learning, because part of the reason we want to figure this out is because it offers the opportunity to learn more data efficient. And in terms of benchmarks, yeah, I agree. We need to figure them out. We need to figure out the protocols. Protocols are super important. But probably at the same time, we need to figure out about definitions of continual learning that we actually care about. And this will help define. I mean, the protocol will define the type of continual learning that you care about. And there are probably going to be several of those, like different types of protocols.
So how do you think we can, can I ask a question? So how do you think
we
can measure the forward transfer progress? So like when I said, I don't think there's anything wrong with comparing against an offline system that was able to shuffle the data, and with this system that had to face it sequentially. But that's not really, that's just going to measure your ability to not do catastrophic, to not forget too much, right? You're not going to do any of the forward transfer stuff. So what's kind of like good tasks where we can set up to actually study the forward transfer? Would you want the system to be more efficient and actually be superior to like something that's trained offline just because it was able to utilize forward transfer? Or do you think that's still not possible? I guess I really like the idea of forward transfer, but so far none of the systems can do it, and I'm not sure how to best assess our expectations for it.
Yeah, I think continuous, forward transfer, continuous transfer learning in this on a sequential way is the critical kind of next thing to really focus on. If you think about things as a inherently sequential streaming paradigm, I think the systems can do far better than offline trained systems, batch systems. And the example sort of I gave earlier of, something changes in the environment and you need to quickly react to that is an example of that. If you think about it as sequential and reacting quickly and, learning quickly based on past experience, you can change something, the entrance to your office is changed, you can react very quickly, but a batch offline system, it would take a long time before that new change becomes a significant percentage of that data set so that the error metrics, pay attention to that and update your representation. Whereas if in a sequential scenario, you can do that learning very, very quickly and update it. So that's an example where a sequential system can be far better than an offline system. And of course, transfer learning, you should be able to learn new things using smaller and smaller number of examples compared to an offline system. So which might require, if you need 1,000 examples of a category in an offline system, but that category is now the 1,000th new category you're learning, maybe you can learn it with just one example. You should not need the full 1,000. So, and again, I think we need benchmarks that focus on these things. We need metrics and evaluation systems and scoring systems that highlight those aspects of it if we're going to really make sure our algorithms focus on those as well. We can't use the standard train and test error metric or test error metrics that we have in offline systems. I think it's a fundamentally new domain, a new way of thinking.
And maybe I wanted to add that, there are actually approaches that have forward transfer, right? It's like you have this list of things, and if you just pick different aspects of it, you can get forward transfer. So in progressive nets, where the capacity of the model grows quadratically with the number of tasks, so it's horrible. You can actually observe forward transfer because that approach doesn't really care about other aspects, so it can do a bit of forward transfer. And yeah, I mean, we could measure it in a standard way. We can look at area under the curve or things like that to see if we're actually learning faster than the other things. I don't think it's impossible. It's just we haven't focused as much. And yeah.
Yeah, one thing I want to point out with this forward transfer as well, I think, Chris, you pointed out, in order to do that well, the system will really need to create representations that are generalizable, representations that are invariant, and that you can either extrapolate to other domains that you couldn't before. And that's going to be that's an implementation detail, but I think that's going to be an important aspect of solving this kind of transfer problem efficiently.
I liked something you said earlier, Subutai, which I interpreted as kind of like as the system ages, as it learns, it should in some ways become more sample efficient. So like somehow it's becoming a more efficient learner as it ages, and that's something I don't think we're measuring really.
Exactly. Yeah. I think that's really, and I think in order to do that, we need, like you were saying earlier, we need to create representations that are inherently invariant and generalizable.
All right, so let's move to the last question of this panel. I would say, okay, I like the panelists' take on bio-inspiration as a viable option to wisely use but not overexploit. I like to think about bio-inspiration at Mars different levels of analysis, and I believe AI and continual learning would benefit most from looking to the brain for an algorithmic computational inspiration rather than implementationally mimicking details of biology, which I believe might not be necessary for AI. I guess it's not a question, just a remark. So do you think adding the capability for learning to forget, it has controlled forgetting, is equally important to learning not to forget, it has avoiding abstract forgetting? How would you think we could develop that, or to add some tools to address that?
Yeah, I think graceful forgetting, figuring out how to do that is important. I think it would be useful to be explicit so that we actually know how forgetting happens in the system. Yeah, how to do this? Well, it's an open question. In the past, we've tried a few things, but they didn't really work, so it doesn't make sense to talk about them. But I do think someone should look into this and come up with. The other issue is benchmarks that we have right now. They're not the right benchmarks for forgetting. Like, you need to have hundreds of tasks for it to become meaningful. You can't do graceful forgetting when you do 10 MNIST tasks or 10 CFAR tasks or whatever. You need hundreds or thousands, and then it becomes a really interesting phenomena to measure.
I think that this point is very important, especially if you look at models that have to learn during a long time, because of course, if you have to learn much more data, you need more room in your model. And by now, any benchmark has a limited amount of data, so we can find some engineering tricks to fit all the data inside the model. But if you want to learn lifelong, then you need to increase capacity dynamically, or on the other hand, you have to find room in your model, so try to delete something. So I think this is a very important topic, especially if we extend our benchmark to work with more data, with more batches. I have no solution right now.
Right. All right, so we couldn't address all the questions that are here in the chat. Of course, I mean, you panelists can look at them if you want. You can answer them in this chat, but we're gonna stop here the panel, and I thank you all for being so great, you panelists, in this panel session, and all the audience here that asked interesting questions. And I think this was great, and it's with panels like these, I think that the field is moving forward and trying to get together and define things that are usable for all of us. So thank you again, and I guess I'll see you again in the next live session. Massimo, do you want to say something?
I just want to drop a quick line.
Right.
So the panel was great. Thanks a lot. And we're hosting another panel in 3 hours. Subutai and Christopher are going to be there as well. So I just wanted to say, if the other panelists want to come back, you are welcome. That's it. Thank you.
Right, absolutely. Thanks, Massimo. And before the Q&A session or next panel, we will hold also the challenge remarks, and we will also I mean, the spotlight talks from the 4 winners of the challenge. So you're all invited to join in a few hours. We will have this live session as well. So thank you again for joining, and I'll see you soon, I hope.
Thank you, Vincenzo, for sharing of
Thank
this
you.
part. Thank you.
Thanks,
Thanks, everyone.
Thank you.
Bye-bye.